So there are certain parts that are literally impossible to hold using a clamp or a vise. But in this week's Fixture Friday, I'm gonna show you how vacuum work holding is often the only option for holding thin, flat work pieces. Let's get started. I was made for this. I was made for this. Okay, so before we get started, let me give you a quick overview. Now, our vacuum work holding systems use high power vacuum to actually pull the parts down to either our grid surface of the base or our customizable top plates, which is what we're gonna talk about today. Now, we currently have 5 different sizes of our chucks, and you can see all of that on our website at Pierson Workholding. But for now, let's take a look at this part. Now, the part that we have here is actually pretty common. It's known as a rack mount panel as a general term. Now, these panels have a standardized width of 19 inches, and they come in different height increments of 1.75 inches. So here we have what is known as a 2U panel, which comes out to 3.5 inches tall. Now, this part has a couple windows, a few holes with big chamfers. I think that's for lights. 7 holes here that are the same size. I'm guessing those are for knobs. And a couple here that are probably for different inputs or larger knobs. And of course, I'm thinking this cutout here is for a power switch. Again, a very type of common thing that we see on these rack mount panels. But when it comes to vacuum work holding, the very first thing I like to do is to look at what type of surface area we're dealing with, specifically the surface area on the bottom of the part. Now, if I come over here, I'm gonna get a quick measurement. Now I'm using Fusion 360, and by just clicking this flat plane, it gives me the area. So using a calculator, 56.5 times 14 gives us 791 pounds of holding force. That's great. Now 14 is the power of a vacuum. Now specifically our Smart Vac system, for every square inch, it will pull that square inch of material down with 14 pounds. Now that 14 pounds is not an actual limitation of our system. This is the actual air pressure around us pushing down on the part, trying to fill in the vacuum of air that we will be removing from under the part. Now, the main rule of thumb is if you can hold a part using a clamp or a vise, you just stop and you do it. Now, this is because clamps and vices have a theoretical unlimited amount of clamping force. Now, the harder you tighten the handle, the higher the clamping force. Of course, it'll break at some point, but still the amount of clamping force is theoretical, whereas vacuum maxes out at that 14 pounds per square inch number. But as I look at this part, it's a decent candidate because we have to machine around the perimeter of the part. We have to poke a bunch of holes in it. And if we had to do chamfers, which we do, we can access them without, again, hitting any clamps or vices along the edges. Now, here's the next thing we need to tackle, because we do have features that break through the part. We can't just machine all the way through, or else once we poke through, we would lose vacuum and the part wouldn't be held with any force at all. So that's where our customizable top plates come into play. Now, I've gone ahead and designed this top plate, and I want to walk you through it right now. And stick around because I've got another tip that will make it even easier than it looks at first glance. Okay, so let me start off with a top view. Now, just to start off, this is a 13.5 by 20 inch top plate. Now, these are off the shelf products that we carry a full stock on. Now, when I first look at this, the way that I like to design is I want to put my part and I want to lock it to the center of the top plate. I've gone ahead and I've already done that. Now, let me hide our workpiece and let me show you the design work that I've done on the top plate. Now, as I hide the part, that reveals a few different grooves that I've cut into the top plate. Now, the grooves in our top plate is what actually creates an airtight seal around every feature that's on the outside of the part or any features that break through. So you can see that it does look complicated, but it's actually pretty easy to do. Let me turn the part back on and give you kind of a see-through view of the part. Now, as I explore around here, you'll see that some of the features that are holes that break through are outside of this gasket groove, highlighted in blue. Now, along the outside is one thing, and then every feature along the inside is a feature that breaks through as well that's also gasketed off. So for example, these windows here, you have the holes, the 3 holes for what I'm assuming are the lights, and then the window for probably like some type of voltage meter that breaks through. All the knobs, and notice that there's a difference between these holes here, this grouping of holes, and these 2 individual holes. Now the grouping of holes, I like to do that because it's best to not individually gasket small holes, because it's actually kind of hard to get our gasket cord stock to wrap around on a round portion and then splice them together perfectly. I prefer to splice them on one continuous straight edge. Now, I did make a top 10 video about this, about the top 10 tips for gasket work holding. I'll link to that. Look for a card up here in the corner or in the description below. But you can see I went with gasketing off these 4 holes and these 3 holes. Then these 2 holes, I could have gone to group them together, but because they're a slightly larger diameter, I'm going to gasket them off because I do want some air to flow in the middle. Now you do see as we zoom out, this odd kind of hole or slot right here. Now that looks weird. I'll explain that a little bit later. But for now, just focus on the gasketing that I've done in the top plate. So now you can see that all the features that break through are going to break through into these areas here. All these areas that are on the outside of the vacuum. Everything in orange here is going to have vacuum work holding applied to it. Now, remember I had that number of the surface area, 791 pounds of holding force. Now that we've created this gasket pattern, this area right here is the actual surface area that the vacuum is going to see. So right now, Fusion is telling me that it's 38.8 square inches. Now I'm going to multiply that times 14 pounds per square inch, and that gives me 543 pounds. Now that's a lot lower because the gasket and all the little things that we've cut out takes away from the surface area. So the name of the game here is to always have to chase after surface area. More surface area means higher holding force. 543 pounds is still pretty good for this part, but we're going to have to adjust our approach so that we can bump up our feeds and speeds and actually stay productive. Now let's take a quick minute to talk about feeds and speeds. Now the enemy of vacuum work holding is not lifting forces from the cutting action. It's actually the side loads created by the cutter entering the part. So the strategy for machining in vacuum work holding applications is light radial depths of cut and normal axial depths, because we're dealing with thin parts. They're not tall. This particular part is only 1/4 inch thick. So we go full depth and light radial loads. Now we want to aim for about 10% of the cutter width, and then we bump up the feeds and speeds so we can zip around the part faster with lighter loads than actually going into the part itself. Now here comes the caution. Now we do have a large flat face that oftentimes people want to remove material down to a specific thickness. But face mills, especially face mills with large diameters, impart massive amounts of side loads. Now, if you needed to face this part down to a dimension, you'd want to do so in a second operation with a couple pins along this back edge of the part. Now, that way, the clockwise direction of the cutter moving from right to left is pushing the part into those pins. We're not minimizing any cutting forces, we're just directing them into pins that are going to add to the rigidity and the security of the entire application. Now, if we didn't have those pins, we would run the risk of the cutter incrementally sliding the part over, and once it gets off of the gasket cord, you have a break in the seal, and that's when your part has a chance of turning into a very nasty frisbee. Now, let me show you one thing that I talked about earlier. So remember this groove here in the middle? It's actually, let me highlight it. It's actually a different depth than the rest of the gasket grooves. Now, if you notice, this gasket groove is not full depth because it breaks through into this through hole. Now, this through hole, if I give you a kind of a wireframe view, this through hole is what introduces vacuum from the chuck surface up through the top plate into this gasket area that I've created. Now, once it flows into there, we add this weird groove to help the vacuum or the air flow across the surface of the part. Now, we do that because there's a chance that parts can self-gasket to the vacuum chuck itself, especially around the small diameter of through hole. So if you are working with a really thin part and it's sitting on the chuck or the top plate, if it were really thin, you might have 100% vacuum at the center, at the through hole, but it might slowly leak and lift up along the edges. We definitely don't want that. So to minimize that, simply adding that groove that kind of snakes its way around the different features is going to create a lot more opportunity for the vacuum to spread across the entire face of the workpiece. Now, another question I get is, okay, I'm gonna drill a through hole, but I want more vacuum. So do more through holes mean higher vacuum? No. And actually, we recommend you only do one through hole. Now, the reason we do this is more through holes, it just means that the airflow through that hole is divided. Like if you have two, it's divided between those two. If you have one, all the air rushes through. Now, our vacuum power unit pulls vacuum on a 1320 chuck in about 1 to 2 seconds. It's going to reach maximum vacuum in just a couple seconds. And adding more through holes could, in theory, increase that, but you couldn't hit turn on the vacuum, close the doors, and hit cycle start in 2 seconds. At least I can't. So one through hole. Now, the other thing is you want to minimize, when you're done with this, you want to minimize the chances for chips or swarf or particles to enter the vacuum system. So one through hole, you can literally like put your finger on it and blow chips off of the top plate. And then when you're done, lift it. That's how you assure good working conditions to not clog the vacuum power unit. Now, quick note, the vacuum power unit can deal with coolant. You're going to ingest coolant. And of course, small particles, swarf-like things. But when things kind of like get clumped up, or if there's a lack of maintenance and someone didn't clean it out after the end of the run, you put it on the shelf. Now you've got coolant that dries those chips, the water evaporates, the coolant concentrate sticks around, and it turns to a really thick sludge that can easily clog the VPU on the first time you run it on the next job. So we will always want to work with a clean working environment. Now, when I poke this through hole through it, how did I pick that? Did I dimension it? Well, no, it's actually just randomly picked, but I randomly pick it to break into this pocketed area. Now, when you do poke through with a drill, you can drill into any one of these 9 pocketed areas. They're just about 50 thousandths deep, and the vacuum from the grid surface of the vacuum chuck flows into these 9 pockets. So anywhere you poke into them, that will assure you will get full vacuum flow to the top side of your part. Now, there's one last thing I want to draw your attention to, because it's a mistake that I intentionally left to show you this illustration. Now I'm going to zoom into these corners and let me give you a good shot of that. Now, when we run our gasket in this groove, you can see that we're kind of doing everything right because our part is gasketed correctly, but there's a difference between these two corners. Now you can see what I did here with this groove. I went around this oblong hole and snaked it around to, again, maximize our surface area. Over here, I didn't, so we kind of have a corner free floating. But here's the truth about this, is that this section right here is not actually going to give you very much vacuum work holding. In fact, you will have your part sitting up high in that section. Now, the reason is there is just not enough surface area to fully compress the gasket that's surrounding that area. I made a feature here, a little quick cut to illustrate. Okay, so this little surface area here, if you can see that, I left some square corners. Fusion is telling me that that is 0.129, let's round up to 0.13 square inches. If we multiply that by 14, that's only 1.82 pounds, I'll give you in ounces, 30 ounces of downward force trying to compress that gasket. 30 ounces is not going to add to the rigidity of the part. It's going to barely be enough to compress that gasket, so it's kind of a wash. So the better thing to do is just cut off the corner as shown up here, so that we can actually skip that bunched up amount of gasket and just go straight to cutting the perimeter. Now keep in mind, this is a 1/4 inch thick, so it's not going to lift, it's not going to do anything crazy. In this case, skip any surface area that could be generated because, once again, it is a wash because it's trying to compress the gasket. Just cut it short. Now there's another section of this part that is along the similar lines, and it's this center section here. This center section, keep in mind, it's between two lengths of gasket. So gasket is going to go in this groove and it's going to go in this groove. Now, when we look at that, we go, well, that's fine. There's going to be vacuum flowing in these areas here. But really, the surface area here is the only surface area that's, again, trying to compress these area of the gasket. Now, I went ahead and took a quick little cut. Fusion is telling me it's 1.7 inches, 1.7 square inches times 14, giving us about 24 pounds. Now, in that section, 24 pounds is definitely enough to compress the gasket in that groove. Now, the rule of thumb is that I like to see, if you're having parallel sets of gasket, I like to see 4 times the gasket diameter width. So that means if we're using an 1/8 inch gasket, 0.125 times 4 is a 1/2 inch. We've actually got 4.8 inches between the gaskets. That's close enough. The bigger principle is you do not want to have very narrow sections between your gasket because there just isn't enough surface area to compress the adjacent gasket. Now, the rule of thumb, again, is to have enough surface area between lengths of gasket to compress it in its groove. Now, I have one last trick I want to show you. So let's go back to the main, let's turn everything on, and we're going to roll forward the time marker, and I'm going to show you one last tip. Now, as I go fully forward, you'll see that I created a pattern out of this. So I created my gasket grooves, my through hole, my air channel slot, and now I patterned it both ways. Now, this is important. Most of the time you would think, oh great, yeah, I'm using the full surface area of my customizable top plate. Yes, but there's one more added bonus of going to multiple pieces. And you'll see when I turn on the stock, we're working from a single large piece of stock. Now we do that because while we're machining one part, say here on the end, we're actually using the cumulative surface area of the other 2 adjacent parts to give stability to this one part. Now, the trick here is to do all the features except on the perimeters. You want to rough machine and leave about 10 to 15 thousandths of material at the bottom of the material. Then your very last cut in the entire machining cycle is to use a finish end mill to go full depth in Z so that we break the parts out. Now remember, we're going to have a very thin foil between the two parts in this section here. Now they're connected, they are going to add stability. When we break through 100% in Z, then we're doing the perimeter cuts along the edges of the part, and then those parts are on their own. Now remember, we had over 500 pounds of surface area. When we approach it from this technique, now we have 1,500 pounds of downward holding force, holding all three parts instead of 500 pounds on each part. It's a little added trick that all the vacuum work holding pros do. So if you're quoting a part, don't quote the individual blank size. Quote larger pieces in which you nest smaller parts within it. Now, let me take a minute here to jump in and show you some really good CAD tips, specifically in Fusion 360. Now, I'm going to open this first sketch where I actually drew it. Now, if you're a Fusion user, you may recognize some of these colors. For example, these purple or lavender ones, that's the projection of the part onto our customizable top plate. Now, I like to have that just so I know what type of geometry I'm working with and then work off of that. Now, in Fusion, one of the most powerful tools you have is parameters. Now, if we open the parameters panel, I created 4 user parameters and I named them OO, which is the offset from the edge of our finished work piece to the edge of the gasket groove itself. I used GW for the gasket width. I used IG and OG for the inside gasket and outside gasket, and these are going to refer to the radiuses that we're going to put on just towards the end of this. Now, why did I name it OO? Well, the best designer is a lazy designer. If you don't care about dimensioning things, you should skip dimensions. Dimension one thing, and if it's similar to another hole, just have an equal constraint. It's always best to kind of declutter your sketches. Now, you can tell that this sketch does look a bit cluttered because I had to go with dimensions to the edges. Now, for example, when I go to select this edge here, so this profile right here is my groove. And then the edge, you can see this formula here, it's OO. And when you do that, it plugs in 30 thousandths of offset. Now, if I ever wanted to change that, I could go into my parameter and I could say, okay, instead of 30 thousandths, let's make it 50 thousandths. And it updates with a little bit of extra edge clearance. Let me Control Z it, that's undo, bring it back out. And I've done that everywhere. Now, to zoom in, I've actually gone around with kind of like these horseshoe shapes around a lot of the holes that break through. Again, we grouped in these 4 features here as just one big box rectangle around them, because I don't want to, again, do individual holes. I want to do sections, gasketed sections. Also did the same thing here, that's identical. I used what's called a center to center slot and opened it up. And again, the gasket groove is another feature, OO. That was my gasket groove. If I wanted to go down in size and change it to maybe our 1/16 inch gasket diameter, I could open gasket width and I could go 062, and you could tell now our gasket is very thin groove. By the way, the formula for your gasket groove, if it's the nominal name is like 1/8 inch, you go 80% for the depth, 95% for the width. So if we plug in the math, if we take 0.125 times 0.95, 95%, it gives us a gasket width of 0.118, 118. If we take 0.125 multiplied by 0.8, it gives us exactly 100 thousandths. That's our gasket groove depth. That's a formula that's similar across all our different gasket sizes, but we always want to push you towards our 1/8 inch, which is the most versatile. Now, let me finish out this sketch. And what I did here in the corners is it's always best to not have sharp corners when you're putting the gasket into these grooves. Now, our gasket material is very soft and pliable. You can turn a sharp 90-degree corner, but it just extends the life of the gasket if there's a slight radius, and it also creates less of an elbow bump. Now, we all have elbows, and when we bend our elbows, we have this little bump that forms right here. Now, when that happens to gasket, it creates a higher surface that the part can sit on, and so you don't get that nice even bottom of the part contact with the top crest of the vacuum gasket. So a slight radius kind of helps out. So as I roll the timeline marker forward, you can see that I have these 2 dimensions. Let me give you a better shot. 2 dimensions of this inside groove, and then when I roll it forward, the outside groove itself. And again, that was specified in my parameters, IG and OG, which is 1/18. And then OG, I plugged in this formula, it's IG plus GW. So basically 1/18 plus whatever our gasket groove width is. So let me change this back to 1/18. And then you can see in the background, it kind of updated. So if you have parts that are kind of like this, vacuum work holding might be a fit for you. So again, check out the 5 different sizes of vacuum systems that we sell at store.piersonworkholding.com, where you can buy everything online 24/7. So until next time, go innovate your production.